Welcome to Pre-Calculus. Today we will investigate writing inverses of logarithmic functions. We'll take a look at two examples. Our first function is this y equals -10 times log of x minus 4. So like we had done when we were writing inverses of exponential functions, when I write inverse of logarithmic functions, I start the same way by switching the domain and the range, which in this case in an equation is switching x and y. So to write the inverse equation, which is my first task, I want to switch x and y. And again, that's equivalent to switching the domain and the range. So my inverse for this logarithmic function is going to be x instead of y equals -10 times logarithm. I'm going to go ahead and write the base. Whenever you see a logarithm that has no base recorded, the implied base is base 10. So I'll actually make it visible there. Of the argument then, instead of x, y minus 4. So that's my inverse. Again, to make that graphable, I need to solve for y. So that's my second step. Now, like we did with the exponentials, I need to get this to a form to where I can make a translation using my key that would go between an exponential and a logarithm. So what I really need to isolate is that log base of the argument. So what I need to move in this equation is the -10. So I'm going to start off by dividing each side by -10. And that'll cancel there on the right. And I'm going to record it here as divided by -10 on the left, but on my next step, I'm going to write that as -1/10 times x. And at that point, that equals log base 10 of the argument y minus 4. So I see at this point that my logarithm base 10 of y minus 4 is by itself. And so now I can make a conversion. So recall that conversion between a logarithm and an exponential. If I have the form of, let's write it as an exponential first, a to the power of x equals, instead of x, let's call that b. A to the power of b equals c. So to convert that to a logarithm, I would say log base a of whatever's on the other side of the equal sign of c equals b. So the direction we'll be going is from this logarithmic form back to the exponential. So just to trace that, it would be, and let me actually, so it's going to be from the base a to the power of whatever's on the equal side equals the c. So we'll make that conversion. For ours, our base is 10. So that's important for us to actually write the base there. So we'll write this as a logarithm as an exponential. So it's 10 to the power of whatever's on the other side. So that's -1/10 times x. So 10 to the power of -1/10 x equals the argument y minus 4. So notice that that conversion put me from a logarithmic equation over into an exponential equation. And I'm ready to finalize this to get my solution for y. All I've got to do is cancel -4 by adding 4 to both sides. And here's my inverse equation. Y equals base 10 to the power of -1/10 x plus 4. And I'll go ahead and box that. So we've written the equation. At this point, what we need to do is graph by making tables. So I'm going to start off, we'll make our table of our original first. So x -10 log of x minus 4. And let's make that with our domain of -2 through positive 2. One thing that we have to be aware of with logarithms is that they won't have any values potentially past the vertical asymptote. So we'll see if this actually catches graphable points or if they're undefined. Let's take this over to Desmos to get a table of values. So I'm going to write the function down, negative 10 log of x minus 4. And we'll grab a table from the graphing calculator. So we'll type that in just as we saw it, y equals negative 10 log of x minus 4. So I see the way that this one's been transformed, at least by the graph, that I'm not going to have any graphable points that are less than positive 4. So I'm going to go ahead and adjust my table. We can see what will happen if we just choose negative 2 through 2. Everything's undefined. So where we need to start is probably with 4. That's my vertical asymptote. 5, 6, 7, and 8. So our entire graph is shifted over to the right. But that's okay. It'll let us get this table now. So we'll just adjust our domain to be 4 through 8. And we'll record these values. So of course at 4, that's the vertical asymptote. It's undefined. At 5, it's at 0. 6 is negative 3.01. 7 is negative 4.77. And 8 is negative 6.02. So we'll just jump back to our notes to finalize this table and sketch the graph of the original. So we'll adjust here. Again, I got to get rid of that domain because those are all undefined points. But if I put 4 through 8, I've got some definition. First one is undefined. That's the vertical asymptote. 5, 0, 6, negative 3.01, 7, negative 4.77, and 8, negative 6.02. We can go ahead and graph that. So I'll start by placing the vertical asymptote at 4. And then at 5, I've got a point at 0. 6 is at negative 3.01, so just a little under negative 3. 7 is negative 4.77. And 8 is negative 6.02. So our function begins from positive infinity and descends, hits the x-axis at 5, and then sweeps over to the right-hand side. Let's get a better curve here. So a nice rough graph there of our original. So at this point, what we want to get is a graph of our inverse equation. So to do that, we could graph on Desmos and get a table separately, or just remembering the relationship between two inverses, I can take this original function and just switch the x column and the y column. So my new x column is going to begin undefined and have the output of 4. Similar to 0, 5, negative 3.016, negative 4.777, and negative 6.028. So it is an unusual way to write the table. We're going from right to left with our x values, but that's okay. We can do it. So at 4, it's undefined, which tells me for this inverse, my asymptote is horizontal. And then at 0, I've got 5. At negative 3.01, I have 6. So negative 3.01 is 6. Negative 4.77 is 7. And negative 6.02 is 8. So that gives me a way to sketch this inverse function. So this one sweeps from above and descends to its horizontal asymptote as it proceeds to positive infinity in the x. Last thing we need to do is to sketch the identity line. So I'll place it, it goes through the origin and has a slope of 1. And recall, we're looking for two key features. If the original and the inverse do intersect, they should intersect on the identity line. And we're seeing that very clearly right at this intersection. They should also show the quality of reflection. So if I were to reflect the original graph across the identity, it will land exactly on the blue graph of the inverse. And that looks just right. So that's our first example. That's a log base 10 function that we wrote the inverse for. Let's head down and take a look at our second example, which is a natural logarithm function. So here I've got y equals natural log of negative 2x cubed minus 1 minus 9. So I want to start with that same task of writing the inverse. And so what will be the same is switching the x and y. What will be different is the solution for y. So we'll just make the inverse by that switch. So instead of y, I'm going to write x equals, and I'm going to put this natural log as log base e. That'll help me in a moment with the conversion to an exponential function. So negative 2, instead of x, I'll write y cubed minus 1 minus 9. So I've got my inverse, and that is technically correct. All I have to do at this point is solve for y. So that's got some doing there, because really I've got y buried in a lot of pieces. But the piece that I need to kind of mind before I make that transition over to an exponential from the logarithm is this log base e of negative 2y cubed minus 1. I need to get that by itself first. So I'm going to start off by adding 9. And so what we've got is x plus 9. Put parentheses because that's going to hang together in the conversion, equals log base e of negative 2y cubed minus 1. So again, what I need at this point is my conversion key. If I've got a logarithm base a of c equals b, the conversion to an exponential would be base a to the power of b equals the argument of the logarithm c. So I want to make that conversion. So for my function, my base that I wrote out, I had to write the base e from the original ln, is going to be e to the power of the other side. So here I'm going left because that's where the other side is. X plus 9 equals negative 2y cubed minus 1. It equals the argument of the logarithm. So that's almost solved for now. At this point, once I've made that conversion, I want to keep my eye on y. That's what I want to solve for. So I need to move the minus 1, the minus 2, and the power of 3. I'll start by adding 1 to cancel the minus 1. And that'll give me e to the power of x plus 9 plus 1 equals negative 2y cubed. So then I want to get rid of this negative 2. I'll divide by negative 2. And I'll divide the whole left side by negative 2 as well. So at this point, I've got e to the power of x plus 9 plus 1, all divided by negative 2. equals y cubed. So we're right there to solve for y. To finalize that, I want to take the cube root. And that gives me my inverse equation of y equals the cube root of the fraction e to the power of x plus 9 plus 1 over negative 2. And that I'm going to box. So we've written the inverse equation. At this point, what I need to do is graph the original and the inverse. So I want to start by making a table. And I won't put the domain at the beginning because I don't really know what part of my domain is going to be undefined for this natural logarithm. So let's go to the graphing calculator first, plug in the function, and then we can decide on our domain based on where that function is defined. So we'll plug in natural log negative 2x cubed minus 1 minus 9. Clear out what we've got here from our previous function. Input our new function. So f of x equals natural log of negative 2x cubed minus 1 minus 9. So there's our function, and it looks like what we can do is create a table that starts much before 0, because it looks like our vertical asymptote, it's not at 0, it looks like it's at a fractional value. But nonetheless, we should adjust our domain so that we're having values before negative 2. In fact, we should probably go to negative 5. So we'll input negative 5, negative 4, and negative 3. And then we don't need all these undefined values. We can stop there at 0. So this is the table that we can use to graph our original. So it's going to be negative 5, negative 3.5, negative 4, negative 4.2, negative 3, negative 5.0, negative 2, negative 6.3, negative 1, negative 9, and then 0 itself is undefined. We just got to keep our eyes on that threshold. All right, so that's what we need from the graphing calculator. Let's head back to our notes. Let's create some room for our table. We'll just recreate what we just saw. So negative 5, negative 4, negative 3, negative 2, negative 1, and 0. 0 was undefined. And then the values again, negative 3.5, negative 4.2, negative 5.0, negative 6.3, and at negative 1, negative 9. So we can graph that now. So negative 5, a lot of this, most of this graph's in quadrant 3 here. Negative 5, negative 3.5, negative 4 is negative 4.2. Negative 3 is negative 5. Negative 2 is negative 6.3. Negative 1 is negative 9. And then I think we've got a vertical asymptote here at a fractional value. So we don't know exactly what it is, but for our purposes here, we're just going to place that vertical asymptote. And then I want to sketch this graph. So this graph descends as it approaches its vertical asymptote towards negative infinity. So at that point, we can graph our inverse by switching the two columns of our table. So remember that basic essential relationship between an inverse and the original is that it's really just a switch of the domain and range. So I'll record our inverse equation, but then for the actual table, I'm just going to take these values and swap them. So negative 3.5 is negative 5. Negative 4.2 is negative 4. Negative 5 is negative 3. Negative 6.3 is negative 2. And negative 9 is negative 1. And then at 0, I'm sorry, let's write this correctly. Undefined x value at 0. So we'll start, let's graph our points in order here. So negative 3.5 is negative 5. Negative 4.2 is negative 4. So we see kind of a close interaction between the graphs here. Negative 5 is negative 3. Negative 6.3 is negative 2. And then negative 9 is negative 1. So our graphs are very close. I'm going to sketch the horizontal asymptote through the fractional value just under the x-axis. So that would correspond with the vertical asymptote. And let's sketch our functions. This function starts close to the horizontal asymptote. Make sure we get a smooth curve in there. And there is our inverse. So very similar functions, the original and the inverse there. So again, I want to place the identity. There's not a whole lot of activity with this pair of functions here in quadrant 1. So I don't see a lot of interaction there. But when I extend the identity line back into quadrant 3, I can see my two key characteristics. The inverse and the original are intersecting right on the identity. And if I were to fold the original over the identity, it would reflect directly onto the graph of its inverse. Well, thank you for joining for an investigation of writing and graphing inverse functions of logarithmic functions. Thank you for joining. See you soon.